myself Prayag Patel, working as assistant professor in IT ICT department of LJ Institute of Engineering and Technology. Now in today's video lecture, I will discuss about the all pair shortest path using dynamic programming algorithm. Here consider the two methods for all pair shortest path algorithm. Now out of these two, consider the first method as a matrix multiplication and shortest path. Now we understand what is all pair shortest path. Now first one is a problem definition. Here consider the given graph as a weighted graph and directed graph. Now here consider weighted graph because here each and every edge considered as a weight, and here consider a direction also. So consider weighted graph and directed graph. Now here all pair shortest path is a problem of determining the shortest path or shortest distance between every pair of vertices in a given graph. Means here you want to find the shortest path, but here consider the all pair shortest path or all point shortest path. Means here find the distance between 1 to 2, minimum distance between 1 to 2, then minimum distance between 1 to 3, then 1 to 4, then 1 to 5. Also you want to find the minimum distance from 2 to remaining all element. Means here from 2 to 1, 2 to 3, 2 to 4, 2 to 5. From 3 to all remaining node, from all 4 to all node, and from 5 to all node. So here consider minimum distance from each and every node to remaining all the nodes. It's called the all point or pair shortest path. Now consider the types of algorithm for all pair shortest path. Here two type of algorithm for all pair shortest path. First one is matrix multiplication and shortest path, and second one consider as a Floyd Russell algorithm. Now we understand one by one. In today's video lecture we discuss about the first method, means matrix multiplication and shortest path. Now here consider the what is the matrix multiplication and how matrix multiplication and shortest path will work. The algorithm is based on dynamic programming. Means you can solve this problem using dynamic programming method, in which each measure loop will invoke an operation that is very similar to matrix multiplication. That's why we can say the matrix multiplication and shortest path. The graph is represented by adjacent matrix where the number of rows and number of columns equal the number of vertices. Means here consider the given graph as a graph, then you represent that graph into matrix in form of matrix. So here consider the matrix dimension consider as a number of row and number of column equal to the total number of vertices. So here consider for example 5 node, then consider 5 row and 5 column. If there is an edge between I to j, then the m of ij equal to wij. Here consider wij means represent the weight of edge between I to j. So here m of ij equal to weight from I to j. Now consider a shortest path p from vertex I to j, and p contains at most m edges. Means if you want to find the distance from I to j, then distance from I to j consider path as a p, then p contain at most m edges. Means here consider m as a 5 edges, 6 edges, like this. The structure of this problem is for any two vertices I and j, if I equal to j, means if you want to find the distance from I to I, so here consider from 1 to 1, then shortest path p from I to j equal to 0. If I not equal to j, means I and j are different element, means 1 to 2, 1 to 3, like this, then the decomposition p into I to k and k to j. So here consider k as an intermediate node, where p dash is a path from I to k. For distance of I to k consider as a p dash as a path, and containing at most m minus 1 edges, and it is the shortest path from I to k. So here consider already find distance from I to k consider as a p dash, and how many number of edges required to reach from I to k consider as a m minus 1 edges, because from I to j consider m edges, so from I to k consider m minus 1 edges. and 1 edge from K to J. So here consider M minus 1 edges. Now consider one example and understand using this example how matrix multiplication and shortest path algorithm will work. So here find this all pair shortest path for given graph using matrix multiplication and shortest path method. Now here say this figure represent one graph. In this graph total 5 nodes, node number 1, 2, 3, 4 and 5. Now here each and every edge represents some weight. So here consider weight as a 3, 4, 2, 8, 7, minus 4, 1, minus 5 and 6 like this. So if you want to find the distance from 1 to 2, then 1 to 3, then 1 to 4, then 1 to 5. Same way you can find the distance from 2 to 1, 2 to 3, 2 to 4, 2 to 5 like this. So how we can solve this? For using dynamic programming method, first step is characterize the structure of an optimal solution. Means you can represent the structure of the equation or formula of the matrix multiplication and shortest path. So here consider first formula is L of I j m equal to 0 if I equal to j and m equal to 0. So here consider the value of m. M means consider the table. Here consider first table, then consider initially as a m equal to 0. Then for the next table consider the m equal to 1. Then consider the next table m equal to 2 like this. So here consider L of I j m equal to 0 if I equal to j and m equal to 0. Means here consider distance from 1 to 1, distance from 2 to 2, distance from 3 to 3 because I equal to j. And consider table as a 0 table because m equal to 0. Then put the value equal to 0. Now consider the another formula L of I j m equal to infinity if I not equal to j and m equal to 0. Means m equal to 0 means consider as an initial step, initial condition, first step. In first step you can represent the distance from 1 to 1, 2 to 2, 3 to 3 up to n equal to 0 and remaining all element consider as an infinity. So here consider L of I j m equal to infinity if I not equal to j, means 1 2, 1 3, 1 4, 1 5 like this. Now consider the next formula, and for this formula consider this figure. Here consider I, k and j. Now if you want to find the distance from I to j, then intermediate node consider as a k. So here represent I to k and then k to j. So what is the formula? Here consider the formula as a L of I j m equal to minimum of L of I j m minus 1 comma minimum of 1 less or equal to k less or equal to and L of I k m minus 1 plus W of kj if m greater than 0. Because m equal to 0, then consider the first and second formula. If m is greater than 0 means for 1 2 3 value consider the last formula L of I j m. Here m means consider the for first step m equal to 1, for next step m equal to 2 like this. If you want to find the first step means L I j 1, then consider minimum of L I j m minus 1 means consider as a L0, means your previous table consider as a L0 and next table consider as a L1. So here consider formula and find the distance from each and every pair. Now consider the second step of the example. Step number 2 is recursively define the value of an optimal solution. So here consider this figure as a given graph. Now according to first step, according to first and second formula, initial condition L of I j m equal to 0 and L of I j m equal to infinity. In according to these two formula, here represent the table like this. So here consider distance from 1 to 1, 2 to 2, 3 to 3, 4 to 4 and 5 to 5 equal to 0 and remaining all distance consider as a infinity as a initial step L0. Here your table name consider as a L0, L1, L2, L3 like this. So here initial table consider as a L0. Now consider the next step. Next step consider as a table L1. Here consider Direct distance means consider only one edge. Remember this point. Here consider table name equal to L1. L1 means 1 means consider only one edge. Remember this point. Now for this table consider the each and every option and find the distance. Here matrix size equal to 5 cross 5 because here total number of node equal to 5. So here consider row number 1, 2, 3, 4 and 5 and consider column number as a 1, 2, 3, 4, 5. Now here in this table each and every node represent 1, 2, 1, 3, 1, 4. What is the meaning of 1, 2? 1, 2 means row number 1, column number 2 means distance from node 1 to node 2 is called the location 1, 2. So here consider first initial location as a 1, 1 but already 1, 1, 2, 2, 3, 3, 4, 4 and 5, 5 equal to 0. So no need to worry about that point. Now next location consider the location L of 1, 2. So here consider location 1, 2 as our next location. Now here what is the value of this location? Initially consider as a infinity. Now in second step you represent the table according to your direct distance because here we write only consider one edge means only consider the direct distance. If the direct distance is available then put the direct distance, otherwise same as infinity. So here consider first as a 1, 2, 2. So here in this figure from node 1 to 2 consider as a distance is 3. So put the value 3, consider this path and put the value 3 in location 1, 2. Now next step is consider the next location row by row means here consider location as a 1, 3. Now in 1, 3 location already given data is infinity. Now according to our formula from node 1 to 3 direct distance is available. Yes. What is the direct distance? 8. So consider this path from 1 to 3 and put the value 8 in our location 1, 3. Means according to this you can fill this table for the direct distance. So here consider next location as a 1, 4. Already given data is infinitive. Now distance from 1 to 4 equal to infinitive because here given data is infinitive and here no path from node 1 to node 4. Direct path is not available from node 1 to 4. Here path from 4 to 1, not 1 to 4. So here consider infinitive as it is. Now next location consider as a location 1, 5. Value of the location 1, 5 equal to -4. So put the value -4 at location 1, 5 because here consider initial value as a infinitive. If the next value or given value or in graph we find the weight of each and every edge. So weight is minimum than infinitive, then you can replace infinitive with that weight. So here consider -4 as our answer. Now consider next location. Here consider 2, 1. Now check the path from 2 to 1 is available. No, here 2 to 1 path is not available. So here put infinitive as it is. Now consider the next location 2, 3 because 2, 2 is already 0. Now 2, 3 consider the path from 2 to 3 is available. In this figure 2 to 3 path is not available. So remain infinitive as it is. Then consider next location 2, 4. 2, 4 value equal to infinitive. Now consider the distance from 2 to 4 or path from 2 to 4 is available in this figure. Yes. So what is the distance? Distance equal to 1. So put the 1 in location 2, 4. Now consider the next location as a 2, 5. Now path from 2 to 5 is available. Yes. Consider this path, red highlighted path, consider as a 2 to 5. So consider this path and distance consider as a 7. So put the 7 at that location. Here in this table, green shaded consider as a updated value and white shaded consider as a same as it is value. Now consider here next point is 3 to 1. For 3 to 1 consider the path from 3 to 1 is available. Here 3 to 1 path is not available. So no any change. Now consider next as a 3 to 2 path is available. Yes. So consider this path 3 to 2 and put the value 4 in this table. Now consider this path from 3 to 2. Now consider next is 3 to 4. 3 to 4 equal to already infinitive. Now path from 3 to 4 is available? No. So remain infinitive as it is. Then next path is 3 to 5. 3 to 5 path is not available, so consider infinitive as it is. Now consider the next row, means row number 4. In row number 4, consider the location for 1. In location for 1, consider the path from 4 to 1 is available. Yes. What is the distance? Distance equal to 2. So put the 2 and consider this path as our 4 to 1 path. Now consider next as a 4 to. In 4 to 2 path is available? No. So move to the next step. 4 3. In 4 3, consider path from 4 to 3 is available? Yes. Then what is the distance? Distance equal to -5. So put the -5 at location 4 3 and consider this path from 4 to 3 as a red highlighted path. So next consider as a location 4 5. In location 4 5, consider the distance. No path is available, so 4 to 5 is infinitive. Now consider last row, row number 5. 5 to 1, consider distance. Here 5 to 1 path is not available, so move to the next step. Here consider 5 to 2. 5 to 2 path is not available because here we consider only direct path. So 5 to 2 path is not available. Next is 5 to 3. 5 to 3 direct path is not available, so consider infinitive as it is. Next is 5 to 4. Here 5 to 4 path is available. Yes. Then consider the distance 6 and put the value 6 in location 5 4 and consider this path from 5 to 4. Now this is considered as our second step. Consider only one node, one edge, means here consider only direct distance and one edge as our selected edge. So here consider this table as a final table after the step number 2. Means consider direct distance and consider this table as our final answer for direct distance. Now consider next step. Remember this point, how you can solve this example. Initially you can represent as a 0 and infinitive, then consider the direct distance, then in next step consider only one node as an intermediate node. Here means one node as an intermediate means you can say that consider two edges. So consider the next step. Consider step number 3, consider one node as intermediate node, means two edges. So here consider the each and every location from 1 to 2, 1 to 3, 1 to 4 up to 5 to 5. Now consider first location 1 to 2. Here 1 to 2 already given data equal to 3, old value equal to 3, means direct distance equal to 3. Now consider the next, here one according to one node as an intermediate, any path is possible. So here consider path as a from 1, move from 1 to 3 and then consider 3 as an intermediate and move from 3 to 2. So here consider 1 to 3 and 3 to 2 as our path. Now what is the total distance for this path? 8 plus 4 equal to 12. So old value equal to 3 and new value equal to 12. Then which is best value or optimal value? Here consider 3 as an optimal value because if you want to find the minimum distance. So here consider 3 as a best value, optimal value. Then no need to change this 3 with 12. So consider 3 as it is. Now consider the next location as a 1 3. Means if you want to find the distance from 1 to 3, then any path is available. Already you find the direct path, but according to one intermediate node, any path is possible or not, you will check that point. So here consider from 1 to 3, any path is possible. According to one intermediate node, no, any path is not possible. So remaining 8 as it is. Now consider the next as a location 1 4. In location 1 4, consider the distance from 1 to 4. Already given distance is infinitive, means direct path is not available. Now find the distance according to one node as an intermediate. Here see in this figure, any possibility are there for find the distance from 1 to 4 using one node as an intermediate, any one node as an intermediate. So here consider two possibilities. First possibility is 1 to 2, then 2 to 4. Means here consider distance as a 3 plus 1 equal to 4. And another possibility is from node number 1 to node number 5, then node number 5 to node number 4. So here two possibilities are there. So here consider our third equation, L of ijm equal to minimum of L of ijm minus 1, minimum 1 less or equal to k less or equal to n, L ik m minus 1 plus wkj. According to this formula, you find the distance of that node 1 to 4. So consider according to our formula, here 1 as a initial point means 1 consider as a I. Now goal state or final state consider as a 4. So consider 4 as a j. Now what is the k? Intermediate node consider as a k. So here consider L of 1 for 2. Here consider 2 means table number 2 because here consider 2 edges. So consider L2. So here consider L1 for 2 equal minimum of L I j m minus 1 means L1 for 1, old value of L1 for. Now next is minimum of 1 less or equal to k less or equal to n, L of ik. Now k means intermediate node. Here consider 2 as an intermediate node as well as 5 as an intermediate node. So consider L of 1 to 1 plus W of 2 4. And second option is L of 1 5 1 plus W of 5 4. So according to this find the value. Now here consider the distance as a initially infinitive as our first value. Now consider next as a L of 1 to 1 equal to already given value in this table as a 3. Now distance W2 4 means consider as a 1. Now consider L15. Here L15 equal to minus 5 in this table and distance W54 equal to 6. According to this we find the value as a minimum of infinitive and 2. So here what is the minimum value? Minimum value equal to 2. So put the value 2 in location 1 4. So here old value is infinitive and new value is 2. Minimum value is 2. So put the 2 at that location. Now consider the next step. Location 1 5. In location 1 5 consider the any path possible from 1 to 5. Not only direct but consider as a one node as an intermediate. So here consider no any one path is available from 1 to 2, then 2 to 5. So here consider this path as a one path is available but old value consider here. So according to our equation consider the old value as a minus 4 and new value as a 3 plus 7. Okay, so here consider minimum of minus 4 and next consider as a 3 plus 7. So here consider 3 as our table value, 7 as a weight, then consider next value as a minimum of minus 4 and 10. So out of these two minimum equal to minus 4. So here consider minus 4 as it is, no need to replace this value because old value is better than new value. So here consider next step as a 2 1 in 2 1, old value consider as an infinitive. Here consider any path is possible from node 2 to 1. Here old value is infinitive means no direct path is available. But for reach 2 to 1, here first path is considered 2 to 4, then 4 to 1. So consider this path and according to our equation consider L212 equal to minimum of L211, minimum of L241 plus W of 41. So consider the value here, then minimum of 1 plus 2. So here consider old value infinitive, 1 value here and 2 from this table in this graph. So here consider 1 plus 2. So minimum of infinitive and 3 consider as a 3 means put the value 3 in our location. Here in place of infinitive we replace the 3. Now according to this we solve all data. Here consider next location as a 2 3. In location 2 3 consider path from 2 to 3. Direct path is not available. Here according to one node as an intermediate consider 2 to 4, then 4 to 3. So according to our formula this is our next step. L23 equal to minimum of L23 and second part is minimum of L24 plus weight of 43. So consider this value means here consider minimum of 1 minus 5. So here consider minus 4. So minimum of infinitive and minus 4 equal to minus 4. So put the value minus 4 at location 2 3. Now next is location 2 4. In location 2 4 already value equal to 1 means direct distance from 2 to 4 equal to 1. Now another way is possible or not. So say in this figure 2 to 5 then 5 to 4. One path is available? Yes. So what is the distance? Here distance equal to 7 plus 6. So here consider value is greater than 1, so no need to change this value. Now consider next location as a location 2, 5. In location 2, 5, direct distance equal to 7. Now another path is possible for reach the 2 to 5. Here no any one edge or one node as an intermediate path is available, so consider 7 as it is. Now next step is 3, 1. In 3, 1, consider the infinitive. 3 to 1 path is not available. Any possibility is there from 3 to 1, one node consider as an intermediate, then no any path from 3 to 1. So infinitive consider as it is. Now next is 3 to 2. In 3 to 2, direct distance is 4. Now consider any another possibilities are there for one intermediate node? No. So consider 4 as it is. Now consider next location as a location 3, 4. Here yellow shaded consider as our current location. So here consider 3, 4 as a next location. So here consider 3, 4, old value equal to infinitive. Now 3 to 4 path is available according to one intermediate node. So here path is available, yes. 3 to 2, then 2 to 4. So here consider old distance as an infinitive and new distance consider as a 4 plus 1 according to our formula. So 4 plus 1 equal to 5 means equal to minimum of infinitive comma 5. So consider minimum equal to 5 and put the value 5 at location 3, 4. Now consider the next location 3, 5. 3 to 5 direct path is not available. Now consider one intermediate path means here consider 3 to 2 and 2 to 5. Now distance consider as a 11. So here consider minimum of infinitive and 11 and minimum equal to 11. So consider 11 as our answer. Now consider next location as a 4, 1. For location 4, 1, old value equal to 2. Then 4 to 1 another path is available. Here consider no any another path is available. So consider the next location as a 4, 2. In 4 to location old value is infinitive. Now 4 to 2 path is available according to one node as an intermediate. So here consider path is available. First path is 4 to 1, then 1 to 2. Another path is 4 to 3, then 3 to 2. So here red lighted consider as our path. So out of these two consider the minimum. So here consider minimum of old value equal to infinitive. New two possibility. First one is 2 plus 3 and second one is minus 5 plus 4. So minimum out of these two consider as a minus 1. So consider minus 1 as a answer and put the minus 1 at location 4, 2. Now consider location 4, 3. Old value equal to minus 5. Now find the path from 4 to 3 is available for consider according to one node as an intermediate. So here consider one path is available 4 to 1, then 1 to 3. So distance is considered as a 8 plus 2 equal to 10 and old distance considered as a minus 5. So consider minus 5 as it is. Now consider the next location as a 4, 5. In 4, 5 consider location first 4 to 1 is first path and then 1 to 5. So consider 2 plus minus 4 means consider as a minus 2. Old value equal to infinitive and new value equal to consider as a minus 2. So minimum consider as a minus 2 and put minus 2 at location 4, 5. Now consider the next as a location 5, 1. And location 5, 1 consider the direct distance is not available but one intermediate distance is possible. Yes, here consider 5 to 4 then 4 to 1. So consider red highlighted path. Here distance is 6 plus 2 equal to 8. So here consider minimum of infinitive and 8 equal to 8. So put the value 8 at location 5, 1. Now consider the next as a 5 to 2 path is available? No. Now any path available that contain only one node as intermediate from 5 to 2 not available. So consider infinitive as it is. Now consider the 5 to 3. In 5 to 3 consider the one node as an intermediate. Path is possible? Yes. 5 to 4 then 4 to 3. Now what is the distance? Distance consider as an infinitive as a old distance and new distance consider as a 6 minus 5. So here consider one distance. So minimum of infinitive and 1 consider as a 1 and put 1. Now consider 5, 4. Location 5, 4 means distance from 5 to 4. Consider one node as an intermediate, no any path available. So consider 6 distance as it is. Now this table consider the path from 1 to all node, 2 to all, 3 to all, means all to all node, and consider only one node as an intermediate. Now our next step is consider the two node as an intermediate node. Now two node as an intermediate node means consider 3 ACs. So here consider next step, step number 4. Consider any two nodes as intermediate node means consider 3 ACs. So consider table name as a L3. Initially L0, then L1, then L2. Here consider L3. Now according to this we find the distance from 1 to 2 and consider the two node as an intermediate node. So here check 1 to 2 path is available for the two intermediate node. So here consider no any path is available from 1 to 2. Direct distance is 3. But according to one intermediate already we find. For according to two intermediate, here no any path from two intermediates. So consider the next location. Next location 1, 3. Consider two node as an intermediate. Then old value here 8. Now consider the path from 1 to 3 and consider two node as an intermediate. Then 1 to 5 is first path, then 5 to 4, then 4 to 3. So here consider 5 and 4 as an intermediate node. So consider distance of this is consider -4 plus 6 plus -5. So here consider according to our formula minimum of 8 means old value, new value consider as a minimum of 2 minus 5. So here consider -3 value. So here consider the according to our table minimum value is 8 minus 3 and minimum equal to -3. So put the -3 at location 1, 3. So here we consider two node as an intermediate node. Now consider next location. Here consider location 1, 4, 1, 5 according to this each and every location. For each and every location you check two node as an intermediate, then possible any path is available or not. If path is available and new distance is minimum than old distance, then you can replace this. Here consider first row only one location or 1, 3 location is changed. Now remaining location is as it is according to our this process. Now in second row value 3, 0, -4 and 1 as it is. Here no any change. So that's why we directly move on the location 2, 5. Only here we consider change location because here consider each and every process according to this. You can perform each and every operation. So here consider next location is a 2, 5. In location 2, 5, 2 to 5 path is available according to two node as an intermediate. So consider here first path 2 to 4, then 4 to 1, then 1 to 5. So here consider the value as a minimum of 7 as a old value, new value consider as a 3 minus 4 because already 1 plus 2 equal to 3 value available in table. So consider 3 minus 4 equal to -1. So minimum of 7 and -1 equal to -1 as a minimum and put the -1 at our location 2, 5. Now consider the next location as a location 3, 1. In location 3, 1 consider the distance from 3 to 1 according to two node as intermediates, then 3 to 2, then 2 to 4, then 4 to 1. So here consider 2 and 4 as an intermediate and distance consider as a minimum of infinitive and minimum of 5 plus 2 equal to 7. So minimum of infinitive and 7 consider 7 as a minimum and put the value 7 at location 3, 1. Now consider the next location. Here all remaining element in row number 3 is as it is because no any path is available, or in some case here distance already given distance is minimum than new distance, so no need to replace. In fourth row all the value are as it is, so no need to worry about that. Now next is row number 5. In row number 5 consider distance from 5 to 2. So here path consider as a 5 to 4, then consider next as a 4 to 3, then consider 3 to 2. So here consider two node and 3 ACs. So here consider distance, old distance as an infinitive, new distance consider as a 1 plus 4 because already 6 minus 5 equal to 1 already we find in table. So 1 plus 4 equal to 5. So minimum of infinitive and 5 consider as a 5 as a minimum. So put the value 5 in this table. Now consider the next location. Here each and every location is compared according to two node as intermediate node. Now this process is continue until the how many number of node or how many number of intermediate node. Here given node or given graph, consider the total 5 nodes. So here consider the 3 node as an intermediate. Maximum consider 3 node as an intermediate because first node consider as a source node and last node consider as a destination node. So remaining 3 node may be intermediate node. So maximum possibility is consider a 3 node as intermediate node. So our next step is consider the 3 node or any 3 node as intermediate node, means you can consider the 4 edges. Now here also we check for each and every location, but here in this video we discuss only the change in which place. So consider the first as a location 1, 2. In location 1, 2, old value is 3. Now consider the new value as a 1 to 5, then 5 to 4, then 4 to 3. So here consider the distance as a 3 as a old distance. Now what is the new distance? New distance consider as a, here consider 3 and next one is minus 3, minus 3 plus 4. So consider the value as a 1 as a final value. So put the value 1 in our location. So here consider the 1 value as a final value and put the 1 in location 1, because old value is 3 and new value is 1. So here consider next location is a location 3, 5, value equal to 11, because all remaining all element or location is same as it is, because old value is better than the new value or new path is not possible. So that's why we directly move on location 3, 5. In location 3, 5 consider the old value as a 11. Now any path is possible. Here consider path from 3 to 5. So first is 3 to 2, then 2 to 4, then consider 4 to 1. So here consider for after 4 to 1 consider 1 to 5. So if you want to find distance from 3 to 5, then consider 2, 4 and 1 as intermediate node. Then what is the distance? Here consider the old distance as a 11 and new distance consider as a 3. So consider 3 as our final answer and put the value 3 in location 3, 5. So here consider this table as a final table. Now in today's lecture we discuss all the steps, means first initially consider the direct distance, then consider the 2 node as an intermediate, 1 node as an intermediate, then consider 2 node as intermediate, then consider 3 node as intermediate. In each and every step you consider each and every location, means 1, 2, 1, 3, 1, 4, 1, 5 like this, each and every step according to each and every node as an intermediate, means 1, 2, 3 like this. So this table consider as our final table for the 3 node as intermediate node. So here consider the final answer of the given graph, means shortest path for all pair shortest path, means distance from each and every node to remaining all the node consider as a this table. So here this is our final answer for method matrix multiplication and shortest path algorithm. Thank you for watching this video.